Welcome back to the series of lectures on high-performance scientific computing. So far, we have had an interesting discussion on how to analyze programs, more specifically parallel programs, using profilers, etc. Now, we will try to see how to go about doing parallel debugging of MPI programs on shared memory machines using open source tools. So first of all, let's just recap ourselves with an introduction to MPI. So MPI, or the message passing interface, is the standardized and portable messaging library used for parallel programming in distributed memory environments or distributed memory machines. The idea of MPI is that it will enable the development of efficient and scalable applications by facilitating communication and coordination between multiple processors running on different cores and on different nodes. But this poses a unique challenge, and the challenge is in debugging. This can become extremely complex due to issues like managing multiple processes, which are obviously running on different nodes and different cores, synchronization issues, non-deterministic behavior, and the need for specialized tools. So now let us look at how do we leverage the right tools and techniques that is essential to identify and resolve issues in MPI applications. So let us first now look at in depth what are the parallel debugging challenges. Firstly, that there are multiple processes, and managing these multiple processes can become quite cumbersome. So debugging MPI programs often requires managing and controlling a large number of parallel processes. We had talked about how MPI processes can scale even up to thousands, if not 100,000s of course. So keeping track of all this and trying to synchronize them can become a challenge. The next thing is that most MPI programs rely heavily on synchronization primitives such as barriers and collective operations like radios. So this can introduce very complex timing and coordination problems that are difficult to debug. And because these codes and processes are running on different machines, they essentially have non-deterministic behavior, because the algorithm itself will work on different parts of data sets. So that is the inherent non-determinism in parallel execution of MPI programs. And plus, they are running on different hardware too, even though the hardware might be exactly same in the sense of model and architecture, but they are physically different machines. So it makes it quite challenging to reproduce and isolate issues. So the program behavior can actually change with every run. There is also the lack of visibility. Debugging MPI programs can be challenging due to the execution of the individual processes and their interactions, and requiring specialized tools and techniques. And obviously, as a number of parallel processes grows, the complexity of these programs increase a lot exponentially, which require scalable tools and these techniques to manage the increased workload. So now let us look what are the few open source debugging tools that are actually available. So you have the GNU debugger, which is a powerful command line debugger which you have studied in the past, and this can be also used to analyze MPI programs at the process level. We have looked at Valgrind. Valgrind is a suite of tools for memory debugging, including memcheck for detecting memory leaks and other issues. You have MUST, which is an MPI unit test. It's a tool for checking the correctness of MPI programs, detecting common programming errors and deadlocks. So on the other side, you also have Scalaska, which is a performance analysis tool for identifying performance bottlenecks in parallel programs, and also the Intel Trace Analyzer and Collector, which is not open source but can still be used. It gives detailed program performance analysis and visualization of MPI program execution. How do we use GDB for MPI processes? So typically, we can start the MPI program with the GDB debugger using the MPI run or MPI exec commands. So when we are calling MPI using MPI run, we can start GDB right from that. Or we can attach GDB to an individual process using GDB's attach command to connect to each MPI process individually. Under Linux, each process will have a unique process ID, and GDB can attach to that specific process ID. Once you have attached or you have started MPI with a GDB process, you can use the extensive range of GDB's commands to manage the execution of each MPI process, such as stepping, setting breakpoints, and inspecting variables, like that was shown in the previous lecture. We need to understand how to work with GDB's process groups to synchronize and coordinate with the debugging of multiple MPI processes. Remember, when this is taking place, you're essentially having multiple programs that are running across multiple cores or multiple nodes, and each of it has to be treated as an individual standalone program to which the GDB process is being done. To debug MPI communication, we need to analyze the flow of communication between MPI processes, identify any issues related to message passing and synchronization. We can also utilize GDB's thread switching commands, which is thread or info threads, to navigate between different MPI processes and inspect their state. You can leverage GDB's breakpoint commands such as break, condition, ignore to set conditional breakpoints and control the execution of multiple MPI processes. We have already looked at data inspection in GDB, where you can use print, display, output to examine variables, arrays, and data structures across different MPI processes to give a snapshot of what is actually going on in your program. The GDB's process control commands like continue, next, and step to navigate the execution of the MPI programs, stepping through the code and observing their behavior, looking at the data at each and every step is still possible. And leveraging GDB's parallel backtracking functionality using backtrace, it can analyze a call stack of multiple MPI processes, identifying the source of any issues. So what are the general good strategies and techniques that one should adopt to do parallel debugging? The first thing we have to look at is step-by-step debugging approach. Establish a methodical process to isolate and reproduce issues. Start with the simplest test cases and gradually increase the complexity. Do extreme logging and tracing. Leverage comprehensive logging and tracing mechanisms to capture critical events, messages, and performance data for the post-mortem analysis. Strategically, you need to place breakpoints in your MPI code to pause their execution and inspect different variables, see how the variables change, how the process states change, and what the communication patterns are. Put in conditional breakpoints to target specific processes, ranks, or execution conditions if you suspect something funny is going on in particular processes. This will enhance the precision of your debugging efforts. And you can also do something very basic, like commonly used techniques like print debugging, code instrumentation, and process isolation to identify what the root cause of the problem is for a program's non-performance. Visualizing parallel execution. The first thing that we need to look is a timeline analysis to see how the MPI process execution takes place. This allows us to identify delays, synchronization issues, and performance bottlenecks. It is a very powerful technique to understand and optimize the performance of parallel applications, which we have seen using the MPIP utility. So we also need to process the communication patterns, analyze the communication patterns between MPI processes, messages exchange, collective operations, point-to-point interactions. We looked at the MPIP profiling tool to gather detailed performance such as CPU utilization, memory usage, and communication overhead for MPI programs. We can also visualize execution traces to gain insights into the dynamic behavior of MPI programs, including process interactions and resource utilization. All this will lead us to a more efficient and scalable MPI program. Common debugging scenarios that we might encounter during debugging parallel MPI programs. One is deadlock scenarios. So we can look at deadlocks which will happen when multiple processes are trying to access the same variable, sometimes not in proper synchronization. So this is where the processes might get stuck waiting for each other, and then you will be unable to proceed. Synchronization errors such as race conditions. We have discussed this in the OpenMP context, but this can happen in the collective communication as well. We can look at GDB, go through the step process. We can then print out the variables as they are stepping through each line of the code and then figure out where these synchronization errors take place. We can use Valgrind to detect memory leaks, essentially to look at unallocated memory or memory which has been not freed, which can result in performance degradation or sometimes even crashes. Incorrect message passing. So sometimes you could have improperly matched MPI send and receive, which results in message passing errors. We must use the tool called MUST to catch such issues if things are going bad. Improper process termination. So sometimes what could happen is that a program might hang or exit unexpectedly if there is a failure in one of the nodes or one of the cores. In this case, the other MPI processes might think that one of the MPI ranks is just frozen in some state and will forever wait for communication. In this, we can use GDB to debug the situation where we can see a particular variable might not be getting updated or a particular MPI function is continuously waiting to receive messages. We can also have improper process termination by the turning off of a node by mistake or a proper power failure of a particular node. We have already discussed Valgrind for memory debugging. We can now know that Valgrind will detect memory leaks for uninitialized memory and other memory related issues in MPI program. Very similar to how we used callgrind, we can use callgrind even with MPI applications where we can analyze the call graph and the performance of these applications. We can integrate Valgrind very well with MPI to see how we can debug memory issues in parallel programs. We can then understand and read the output from the output files generated by Valgrind for MPI applications very similarly to how we did it for the serial code. What is MUST or MPI unit test? MPI unit test is an open source tool for checking the correctness of MPI programs. So MPI performs static and dynamic analysis to detect common MPI programming errors such as deadlocks, resource leaks, and incorrect collective operations. MUST can be easily integrated into the debugging workflow, allowing developers to quickly identify and address correctness issues in their MPI applications. It supports a wide range of MPI functions and provides detailed error reports, helping developers to pinpoint the root cause of correctness problems. By using MUST in conjunction with other parallel debugging tools such as GDP, you can now get comprehensive debugging for their MPI programs. Lastly, we have to really look at how to debug parallel input-output. We have to understand how the MPI input-output interface looks like, which MPI I/O functions and their usage identify potential issues during parallel file operations. Remember, when you're writing files to a disk, multiple processes might be trying to write to the same particular file, and this brings in a synchronization challenge. So we need to look at it in terms of file access and data consistency in parallel I/O operations to avoid race conditions and data corruption of the files on disk. Usually, these files are mounted over network attached storage, so all MPI ranks typically have access to these files, and then I/O then becomes a challenge. We can utilize debugging tools like MPI I/O and ADA I/O trace to detect and diagnose parallel I/O issues such as deadlocks, hangs, and data inconsistencies. We also should investigate the file access patterns of MPI process to identify potential hotspots, load imbalances, and inefficient I/O strategies that may lead to performance bottlenecks. Using profiling and tracing tools such as Vampire or Scalaska to gain a deeper understanding of the parallel I/O behavior, including collective I/O operations, data distribution, and file system interactions. Collective operations. It is very important to debug collective MPI operations. So first of all, we need to understand what are the different types of MPI collective operations that we have, such as broadcast, gather, scatter, reduce, and all reduce. and how they impact the debugging process. We know that the collective operations require strict synchronization between the participating processes, and debugging these operations can be challenging due to potential deadlocks, hangs, and other synchronization related problems. Visual tools like Vampir, Paravar, and Scalascar usually visualize the execution of these collective operations, allowing you to identify communication patterns, process interactions, and other potential bottlenecks. GDB commands specific to collective operations such as info threads and thread apply all understand the state of each participating process and the overall synchronization status. And obviously, we can use logging and tracing mechanisms to capture detailed information about the execution of the collective operations, including timestamps, process IDs, data exchange, to aid in the debugging process. What are the unique challenges of hybrid parallelism? So, debugging MPI programs that combine multiple parallelism paradigms such as MPI and OpenMP or MPI and CUDA, codes which we have discussed, can introduce additional complexities due to the interplay between different runtime systems and the program models. What we really need to do is ensure proper synchronization and communication between the MPI process and the underlying parallel constructs, either OpenMP threads or CUDA kernels, to avoid deadlocks, race conditions, and other concurrency related issues. We should use tools that can provide a comprehensive view of the hybrid program's execution, including performance metrics, communication patterns, and resource utilization across the different parallelism layers. We need to identify and resolve deadlocks that can occur due to the interaction between MPI process and the underlying parallel construct, which may require specialized debugging techniques and the ability to step through the execution at multiple levels. We can ensure a seamless integration of debugging tools like GDB, CUDA GDB to handle the hybrid nature of the program, allowing developers to debug the MPI layer and the underlying parallel construct, which could be CUDA or OpenMP simultaneously. What happens on HPC clusters? So far we have been talking in general, but on HPC cluster architectures, they usually have specialized hardware and configurations with accelerators, high-speed interconnects. They have complex node topologies which require tailored debugging approaches. Debugging on HPC clusters may also be limited by limited availability of resources such as memory, CPU, and storage, which necessitate efficient debugging techniques and tools. Debugging an MPI program on large-scale HPC clusters can be challenging due to the increased number of processes and potential synchronization issues requiring special tools and strategies. On HPC clusters, typically there are job scheduling applications. So integrating the debugging process with the cluster's job scheduling and resource allocation system is crucial for seamless debugging workflows. Often, you have to do remote debugging for MPI programs on HPC clusters, as it is possibly not feasible for you to be right next to the HPC cluster while you're trying to do the analysis. Logging and tracing. Comprehensive logging and tracing mechanisms are essential for understanding and debugging MPI programs running on HPC clusters, where the scale and complexity can obscure issues. One thing that can be done is automated debugging and continuous integration. So if you integrate debugging tools in your development pipelines, you can leverage automated testing frameworks for continuous integration pipelines and seamlessly incorporate parallel debugging tools in the development workflow. You can put in automated regression testing. So this is basically implement a regression testing suite that automatically runs on parallel debugging tools such as GDB, Valgrind, and Must to catch issues early in the development cycle. We can integrate tools for visualizing the execution of MPI processes, including timeline analysis, process communication patterns, and the performance profiling, and into the CI/CD pipeline. Streamline the reporting and issue tracking the process by integrating parallel debugging tool outputs with a bug tracking system and collaboration platforms. We can also try to leverage containerization and cloud-based platforms to ensure consistent and scalable parallel debugging environments within the pipeline. What seem to be the emerging trends and the future developments in parallel debugging? One is machine learning based debugging. So where we use machine learning and AI techniques to automate the debugging process, identify patterns, and sort of provide intelligent insights. So now a lot of cloud-hosted debugging solutions offer scalable resources, remote access, and collaborative features for parallel debugging. Seamless integration of open source debugging tools like GDB, Valgrind, and Must with other development tools and frameworks are sort of required for a more comprehensive debugging experience. Improved visualization, performance analysis, and runtime monitoring capabilities to gain deeper insights into the behavior of parallel MPI programs. And finally, we need to exploit containerization for the maximum portability. This portability should come with reproducibility as well and not at the cost of it. So, what are the key conclusions and takeaways from this video? To master parallel debugging skills, it is really crucial to understand high performance computing and distributed systems. We need to really leverage open source tools like GDB, Valgrind, and Must. We should have very good debugging strategies and techniques, best practices, and step-by-step approaches for effectively debugging the MPI program. We have to put in approaches like logging, tracing, and common troubleshooting techniques. It is better to integrate debugging into development workflows because we need to come up with automated testing frameworks for continuous integration pipelines, and this will streamline the development and maintenance of MPI programs. So these are the emerging trends and future developments for parallel debugging. Thank you.